In this video, we're going to talk about a very specific kind of galvanic cells, which they may not be very intuitive once you first are introduced to it, but it should make sense as we try to understand the the deeper meaning of it. Those are the concentration cells. The concentration cells are a specific kind of galvanic cells where the reaction in the anode and the reaction in the cathode are the same but reversed. And the whole purpose of that concentration cell is to make the concentrations of ions on both solutions, the anode and the cathode, the same. So let me give you an example. If you connect a beaker in which there is a 0,1 molar solution of copper 2 plus, and you dip the copper electrode in it, and the other solution has a beaker of 1 molar copper 2 plus. What you will see is a current of electrons from your anode to the cathode, as usual, so that it evolves until the concentrations of copper 2 plus are equal on both beakers. This is called a concentration cell. So let's try to understand what exactly is going on here. So in your anode, the oxidation is that copper in the anode becomes copper 2 plus in the anode. And the reduction, the copper 2 plus in the cathode becomes copper in the cathode. So sure, this has whatever the standard cell potential, standard half reaction this is negative or this is positive, but the overall standard is 0. So the only thing that makes concentration cells move is the difference in concentration. The overall, as you can see, is just a net move of, so copper anode will disappear, the copper 2 plus from the cathode will disappear to become copper 2 plus in the anode and copper in the cathode. So how can we quantify this? Well, applying the Nernst equation, RT in this case is 2F logarithm of what? Logarithm of reactant, concentration of reactants. This is a solid, so I'm going to put concentration of copper in the cathode and concentration as products, concentration of copper in the anode. Okay, this is 0 as we said, because the reaction in the cathode and in the anode is the same but reversed. So in standard conditions this potential would be 0. This potential is not 0 provided that the concentrations in the cathode and the anode are not the same. So you can think of this phenomenon as the same phenomenon as osmosis, if you will. The tendency when you have a bilipid membrane and you have a concentration of sodium on one side, a concentration of sodium on the other, there is, whenever there's a gradient, there's a potential, there is a tendency for those two concentrations to be equal, and that's what moves the sodium-potassium pumps that you are very much aware of. And so this can be thought in this case, just that if you connect the two beakers with a wire, you can see voltage being measured and therefore conduction of electrons and some current that you can use. Typically these are very small, as you can see, because it's under a logarithm. You would need to create a large difference of concentrations to see something that is remarkable. Let me remind you that typically the standard cell potentials is the order of 1 volt, and here we have 0.02 or 0.03 volts. So while it is not a large potential, what you will see is a transfer of electrons, so that the objective is that the concentrations on both sides are the same. Okay, take home message: this is always 0 for concentration cells. What creates the potential is the difference in concentrations. So let's try to solve another problem. Like in this case, we are being told we have a concentration cell with silver and silver plus, and let's say that in one you have some silver, and the concentration in this case is 0.01 molar of silver plus, and in the other one you have another electrode of silver, and the concentration, this silver, the concentration is 4.0 times 10 to the negative 4. Okay, so there's less in here, so you want, when you connect these, well, what it's asking you is what is the cell potential. So we can just apply the Nernst equation, RT and F. So, and remember that, so you will see there has to be an increase, so there will be a flow of electrons from right to left, and here you want to increase the concentration, so you will have this, so that the concentration is products. This will be your anode, and in here you will see plus 1 electron. This will be your cathode. Okay, so this will be the reactants 0.01 molar, the products 4.0 times 10 to the negative 4. Notice that the number of electrons is 1, so just 1 times F, logarithm of concentration of products. Concentration of products, it's in the anode, so this will be, no need for brackets, 4.0 times 10 to the negative 4 molar, and concentrations of reactants is 0.01 molar. Okay, this is 0, so notice that the way we have written this, because this is larger, logarithm of a number smaller than 1 will be negative, negative, negative. This will be positive. The reaction as we have written it will move forward. Until when? Until you reach the concentrations in equilibrium. What are the concentrations in equilibrium? Well, when the two concentrations are equivalent. And when is that going to be? Well, when you have equal concentrations on reactants and products, which you can just do the average. So this is 4 times 10 to the negative 4 plus 0.01, you divide by 2. This will be the concentrations in the cathode and in the anode once this concentration cell dies. That is, the concentrations on both sides are equivalent.